Hello everyone. In this video, I'm going to talk about the homogeneous linear equations and retrieve the general solution. This is part of from the textbook we're using, um, chapter 4, which is about linear second order equations. And previous videos talked about the introduction to the mass spring oscillator, right? I'm going to try to balance between the background and the examples, then do another video for examples. So this is not just a video going right to examples, like this is how you solve, and here is an example. More kind of getting some background and because also it can be extensive, I'll do the best in balancing that. If there is something that may need some little bit retrieval, I'll ask you to pause the video and try it on your own, something like that. So the video as well is not too long, but all right, let's work on it. So here the idea, of course, we have a second order, and it goes this way. See why? Not yet. So as I mentioned in the other video, that this goes as inertia times second derivative, the damping times first derivative, and the stiffness times the function. And here are the external forces. So the special case that this video is about is when f of t equals 0, which means there are no external forces, which means for the system, that is the, let's abbreviate this way, the mass spring oscillator kind of vibrating freely, right? Vibrating freely. It's important to understand vibrating freely doesn't mean it keeps going on all the time, nonstop or something. It just means no external forces. But we saw the other cases have to do with the damping. All right. So if if that happens, then now let's give it this way. And this is what's called the homogeneous equation. All right. Just a quick note that here, if you want uh, to the textbook, you probably in other sections that are not covered so far, you may seen this here, but they're not related. Let's say homogeneous equation in chapter 2 previously somewhere else, but that has to do with in the first order, of course. So this is the differential equation. But in that section, the definition of homogeneous first order talks about that you can write this in terms of y over x, kind of this ratio. Um, let's just give you an example. Doesn't mean that it's only y over x, but there is an example. Let's say you're given a function and you play with it and you find out that this is can be written this form. All right, so that's something else. For second order, of course, here linear differential equation is called homogeneous when external forces are not there or not considered. All right. So one thing that we know with this type of equation is we expect the solution to have some linear combination of or some linear combination. And of course, that involves the second derivative and the first derivative. So here we must have the property that the second derivative is expressible in terms um, of linear combination of the first derivative and the function, or we say zero derivative. So let's write it down of a linear first derivative. And if you haven't seen this, sometimes not discussed in other courses, zero derivatives. What does this mean? It just, for example, the zeroth derivative of a function is itself, right? So, for example, if somebody says f of x squared, what is the zero derivative of itself? All right. So this is just to talk about that we know these type of equations and we have an idea of what requirement that we must have as far as the second derivative and the combination in relation to the first and the zero derivative. And also, like we did in the past, we used kind of guess, kind of guess a solution, let's say here in the form of y equal ERT, and other possible solutions, and see if they actually satisfy the equation. And why would we guess this? Because when you take a derivative, right, this gives you only kind of like, let's say you go to the first one, it's just going to be some multiple times that derivative. And that will kind of give us the understanding that this may be a possible solution. So let's do that. Let's see. We know what the first derivative is and what the second one. Let's see if that works. So let's substitute into the equation, right? Let's use it here and see if it works. All right, let's check. So If you do this, you have A, then you have second derivative, right? Um, so the next one will be R times R square ERT. So R square ERT plus PR ERT, the first one, plus C times ERT. Right? So this is y prime, C y prime. So let's check. Do they give us 0? ERT is a common factor. AR squared plus BR plus C equals 0. And of course, we know from exponential function that this cannot be 0. So this, um, or we divide now that it cannot be 0, we can divide by it, and this gives us 0, which means that e to this exponent RT is a solution, of course, if and only if AR squared plus BR plus C equals 0. And this is a quadratic equation that we know how to solve. Let's say it could be just R written the way it is, or over here let's specify where. Let's separate them. Let's write here, you're used to negative B plus minus B squared minus 4AC all over 2A. Okay, so this, let's say R1 and R2. And it's possible that it can, of course, be 0. And when it can be 0, that means you have these R1 and R2 are figured out. So here you're going to run into the cases. You may have R1 and R2 are real and distinct, right? When that happens, when the discriminant is positive. And of course, we know that R1 and R2 are not distinct. R1, R2 are equal, real, and equal if the discriminant is 0. And we know that R1, R2 are complex conjugates when the discriminant is negative. So here we can examine this and study it. But we know we can start with this here and build this up. And this tells us that this needs to be 0, which is called the auxiliary equation. So this is auxiliary equation. Of course, some books will also call it maybe characteristic equation. Let's wrap this in an example. All right. Find a pair of solution or solutions to this second order linear equation. All right. So let's propose that the solution must be the ERT. So these auxiliary equation must be, that's why I showed you that beginning, so you see where these characteristic equation also called come from. So when you do here r squared plus 5r minus 6 equals 0, it's clear where it came from. We know how to do this factor. Then we get r equal 1 and r equal negative 6. And that tells us that if we do RT, right, T, and negative 60, RT again, are solutions. So you can try this. You can now take one of them, differentiate twice, substitute, see if you get 0, try the second one, and that will work. Then, and of course, you'll say, is this it? Let's talk more, right? So this is kind of like the idea to start with. Then let's put a note that, of course, you can realize that if a function is identical to 0, is also gonna work, is also a solution, right? To that second order homogeneous equation. What else we can say? Furthermore, actually, when we have a pair of solutions to this equation, like we did now, we can construct an infinite number of other solutions. It works out this way. If we have this pair let's write it first. If we have this pair of solutions, we can construct infinite number of solutions. And how? What do you think? You've seen linear combinations, and if you've done vectors, you, you know what the linear combinations are. So how? Of course, by forming linear combinations, forming linear combinations. So the idea is this. Plus C2 by 2t, which means for the previous, this means that for the previous example, I can construct something like this, right? We have here. Right, we can construct this and we can check whether this is a solution. So this is, as I mentioned, to balance between giving you the details and also asking you to check. Would you take this and check it in all right, check in that and see whether it gives you a solution. All right, so one thing you're gonna notice, and here I will connect the two, so we can connect it with what we did in the past. If this happens, you see C1 and C2, and you're asked um, kind of 2 degrees of freedom, C1 and C2 in this combination, right? How can we solve for this? Um, of course, the physics and the other examples you've done in the past, if you have 2 degrees of freedom, you need kind of 2 equations or something like that. So here you will need, just like what we did in the past, initial value problem for this second order equation using 2 initial conditions. So, so, so we need to explore more, and let's do an example to talk a little more about this. Um, let's solve the IVP. So I think up to now, you saw what happens. So summarize. Uh, we we're talking about this auxiliary equation or characteristic equation, and we gave that something special must happen, and this function y equal exponential rt, if we gave it as one of the solutions, we run into this characteristic equation. So ERT is only a solution if and only if this equals to 0. So now we're going to explore the cases where this auxiliary equation equals to 0. And of course, the first thing to talk about is this. Then second thing is this. Then next one is this one. Right. So in this example, we solved and we found 2 solutions, and we're like, the combination of these, of course, there is something I'll talk about after, is linearly independent for these solutions. Um, uh, when you put them in linear combination, they're also a solution. But that means you have 2 degrees of freedom, so we need to go into the IVP. All right, let's do this example. All right, so here, as I mentioned, probably not to show a lot of details, but still connect to get the understanding on why now we're doing this and we do it for linear equations, right? Just like in algebra, why you're solving a quadratic equation with, let's say, quadratic formula or factoring or complete square or something like that. But when you had linear equation, you didn't do that. So I think that's the understanding we need to get into. All right, so we will first find a pair of solutions in the previous example. We will adjust the constant C1 and C2 to obtain the solution. Auxiliary is R squared plus 2R minus 1 equals 0. So you see now, looking at it now, and like, we know where it came from. So using the quadratic formula, you get R1, this, and R2. So pause the video and check them out and simplify and see if that's what you get. So this gives us the linear combination that I mentioned, C1e to R1, which is this T, and plus C2e to R2 T. So of course now, to find the specific solution that satisfies this initial value problem, we need to go into the initial conditions. So now for a specific solution. All right, so we're going to use the first initial condition into that, the whole thing is 0. And we did something like this when we checked ET or something in whether it's a solution. All right, and second one there. Of course, we will find the first derivative to this, right? So here I put find y prime of t. Okay. Now use it here. You should get okay. So these two equations give us C1 plus C2 equals 0 from the initial condition, right? So it's 0 because of this, then this would be 1. Then the second one, negative 1. Did I put 1? Negative 1. Let's copy it correctly the way this one is. Okay. Negative 1. So C1 for negative C2. Let's put it here. Negative C2, C1. And here we're used to distribute. I'm not gonna distribute. I'm actually going to factor C2. Then I will have negative with negative and negative with positive and negative 1. This is just positive this way. And this is out. And this is negative 2 square root of 2 times C2. For negative 1, which is C2, is negative 1 over negative 2 square root of 2. Rationalize, simplify, square root of 2 over 4, which gives us C1 to be negative square root of 2 over 4 for C1. All right, so here it is. The specific or particular solution to this. All right, that's the solution that we want. And now we understand kind of how this works. So kind of to gain more insight, I'm going to give you some ideas here, some theory behind these here, and talk about independence before I go for repeated and conclude the video. All right, so some other things you need to understand. So yeah, for a theorem, if you have real numbers, of course, A, remember, can't be 0 because if it's 0, then it's not a second order. So there is a theorem that says that if you have, let's write it down. And now you're familiar with this, even though they look abstract, they're just the initial conditions and the homogeneous equation. And so let's say you have A, of course, not zero, and B and C and T naught and Y naught there and Y1, right? So they are, of course, all real numbers. Uh, so for this, there actually this theorem says there exists a unique solution. So this is the first theorem. Um, there exists a unique solution to this IVP. And that's nice to know because we're looking for the existence and the uniqueness solution for these homogeneous case. So it's good to know that, yeah, there exists a unique solution, and not only it exists, it is valid, or it is valid for all uh, t belonging to infinity to positive infinity. So that's good to know, and that kind of gives us relief. So we're like, does it even exist, or am I wasting time? So let's give you kind of a definition, and I'll call it definition one. So a pair of you have a pair. Uh, of course, if you want to see all the wiring, you can just check the textbook or any linear or any differential equation book. Um, but I would say it with what I try to simplify here. So a pair of y1t and y2t, uh, of course, y sub 1 and y sub 2. Their functions, they're dependent on t. They are said to be linearly independent on some interval I, if and only if neither of them is a constant multiple of the other. If and only if um, neither of them and I think, of course, in the past you've seen with kind of equations, lines, right? And I think when you've seen these in algebra, you talked about consistent independent, just kind of bring the memory to the past. Some linearly independent. Um, so in the past, like something consistent, independent. If you get a case like this, then you know you have a solution. But if you have something like this, then you say consistent dependent. Right. And of course, if you have this, then it's, I don't know, then you say inconsistent. So here, coming back to this, linearly independent means if one cannot be expressed as a constant multiple of the other one. All right, so we will say y1 and y2 are linearly independent if one of them linearly dependent. That means now if we reverse this, linearly dependent if one can be a constant multiple of the other. All right. So let's give you theorem 2. Theorem 2, of course, if you have these two functions and there are two solutions, of a differential equation, these homogeneous solutions of this differential equation, and they are linearly independent, and are let's see, linearly independent. Let's do this way. Linearly independent, and they are linearly independent, then this theorem guarantees that C1 and then C1 and C2 kind of unique constants can always be found. So that's another nice theorem, because once the theorem says it, then it's a fact, right? So it can always be found, so that and when we need them, of course, so that C1, Y1 sub 1 T and C2, Y2 sub Y sub 2 T here is a solution. To IVP. All right, so this theorem 2 is about representation of solutions to initial value problem, right? Is about representation of solution to the value problem. And this comes something that's nice, and you will need for other differential equation courses, is this lemma here, which is kind of an introductory theorem. And it's about Wronskian. And it says here for any, of course, as I mentioned, the A and the B and the C, Y2 are and Y1 are any two solutions for the equation if the Wronskian if Y1, I'll just put, here they put tau, but I'll just put T to make it easier. Let's see. And this is called the Wronskian. And I will give you probably some more ideas about it, but it comes very handy in even grad courses that have to do with differential equations. So it's good to know at this stage, and maybe the symbol for it. will be this way. State independent variable. All right, so this Wronskian holds at any t on any t. Of course, the same thing I mentioned because this is a lemma one. So what I mentioned about the A and B and C, you carry here, and so and this what this is, what's the main thing that is helpful here to know, or a fact to know, then y1 and y2 are linearly independent. All right. So the expression here on the left, of course, as I put for you, so Wronskian, there are some examples where you can check this or prove it as well. There is in the book a proof to the lemma one, and which carries and helps in the proof of the theorem two. Right, and that and these two are very helpful. So I think this is really useful to know that if you have this Wronskian, and of course you can set it up as a matrix, if we will talk about that later, then or then this we get this. Okay, so let's talk about, I think, distinct real roots. Then or yeah, let's talk about distinct real roots here, and finish this video, then do the other cases in different video. All right, so let's distinct real roots. So we're gonna go to which one here? So kind of discussed here. Now let's talk about this one. Or not yet. Uh, Not yet. Let's finish distinct real roots. Then I will do the equal roots after this. Let's summarize distinct real roots, then talk about repeated roots. Yeah, so let's summarize this. I think it's better before we go into the repeated roots, but just kind of show you in general that you know, kind of the thought behind uh, deriving and figuring out the type of solutions that are needed. What once you set up a case of homogeneous case, right? Once you set it up and you propose this, and that leads you to this, right? And that leads you to these types. So now, as we talked about the distinct, let's go ahead and just say, yeah, so if there is a video just solving problems, now this is what you would use: distinct real roots. It will say if the auxiliary equation has distinct roots, so f, let's write it, um, has distinct roots R1 and R2, then both E2 R1T and of course T and Y sub 2 T here is T R2T are solutions to the differential equation that is homogeneous, are solutions, and this is a general solution. All right, so the auxiliary equation is the one we use the R's. It comes from the homogeneous equation. So if that has two distinct roots, R1 and R2, then you can go ahead and mention that these two are solutions, and the linear combination form the general solution. All right, so I think this is the important part here. All right, so repeated root, kind of just the idea, there isn't much to say here, but maybe we'll do the examples. Repeated root. Same thing you will run, but I'll just give you here the same kind of conclusion once you work on it. When this is what I mentioned to balance, we can go ahead and check all that I'm going to mention. If the auxiliary equation has repeated root, then both y sub 1 of t equal ERT and y sub 2 of t equal some function of t. So here we pick t, ERT or E2 RT are solutions. And you can, of course, check them. That's what I mentioned to pause the video, and you can now do the substitution that we've done. And we learned that because these are linearly independent, we learned that y of t, of course, here will give us is a general solution. And we can do this, we can check it, and I think I'll do another video in which we check this. If you want here an example, maybe if we can do one quickly. Let's say to find the solution for this, kind of give you the background quickly, then maybe do details in other examples. Of course, you need here two initial conditions. So now you see that you're going to go into many also call it characteristic equation, which we find that this is perfect square which are equal -2, so we run into this repeated root, right? And since it's a repeated root, it means y1 is this with the r, and y2 is this. And here I'll also ask you to check, and you're going to find that it works. So based on the previous examples, I encourage you to try this one, um, because you know what you need to do, because that's kind of one of my ideas in the videos, is for you to kind of build the thought and the strategy in mind, not think about it as mechanical all the time or something like that. So you will say, um, I have the function, let's say y2, and I can find its derivative, first one, and find its second derivative. What if I plug in, um, excuse me, the first one, second one, and the function into the equation? Will I get 0? All right. So, so you can try this as a check into here, of course, using y um, sub 1 and first derivative and second derivative, right? Then you can do the same thing here. You can find the first derivative and the second one and use here. In both cases, you get 0, which will prove for you that when it is repeated, putting a function of this independent variable here works. So not necessarily thinking that it's ERT and ERT, something like that, or e to the exponent RT, and the same. Then, so that's kind of the build up to this. And when you do this exercise, you're going to see that it works. Then, just like we did with previous examples, you can move on to the next step, which is the general solution. And find C1 and C2. So we do have the initial conditions, right? And when you use the first one here, you will get, just like the other example, C1 plus C2 equal 1, because e power 0 here and e power 0 there. Then using the other initial condition, you will get, when you do the derivative, so you want to find the derivative of this, right? Then use the condition and try it. You should get -2C1, and of course the e power 0 will be there, plus C2 and e power 0 will be there, minus 2C2 times 0 times e power 0 will be there, equal to 3, all right, which is And that will give you C1 as 1 and C2 as 5, and will make this general solution to be this. Okay, so it's a solution. It's a kind of specific solution, of course, to the IVP. I think I'll stop here, and in other videos, we'll do some examples. But I'm trying to give you here the concept so you can understand this concept in general. When it comes to repeated roots, you're going to propose these two solutions, and there is a linear combination that comes, and you will need the initial conditions to find C1 and C2. So once you get y, you find y prime and you use the other initial condition, and that gives you that. All right, thank you.